Hello, I'm Victor. I'm an astrophysics major. Today I'm going to talk about eigenvectors and eigenvalues and a bit about rotations in the plane. I have this website, it's quite interesting, it's about learning physics. You should look at it. Okay, we begin by explaining what eigen means. It comes from German, it means on or south. This makes sense because if this is a matrix corresponding to a linear transformation, then this vector after the transformation goes to another vector that it's in the same span, it's in its own span. This condition, it seems arbitrary, but it's quite remarkable. It appears in many parts of physics. We begin by the definition. We multiply both sides, if you want, by the identity matrix. This is just going to be itself. This is going to be identity times the right-hand side here. Then we factor out the eigenvector. Why? Because then we can find the eigenvalues by noticing this. This eigenvector, we want to find its non-trivial solutions because we know that it can just be zero, and that works. But if we find the non-trivial solutions, that means that this matrix is singular, it is non-invertible. So this determinant should be equal to zero. This determinant is going to yield this characteristic polynomial, and the zeros of said polynomial are going to give you the eigenvalues. Once you have the eigenvalues, you can find the eigenvectors. You plug in the corresponding eigenvalues to the corresponding eigenvectors, and then you solve for the eigenvectors. How do you solve for them? Well, this is a homogeneous system. Because it is a homogeneous system, any eigenvector is going to be a member of the null space of this matrix. Therefore, it's a matter of finding the null space or reducing and finding the solutions for the eigenvector x. Now I'm going to introduce rotations in the plane. You can think that this is I hat and this is j hat. So how do you get this part? Well, this is polar coordinates. J hat is orthogonal to I hat, so use derive. That's going to give you the orthogonal component. That's why this matrix represents rotation in the 2D plane. You plug in theta equals to pi over 2, you get this matrix for which you're going to find the eigenvalues and eigenvectors. Once you do the process I said before, you find that said eigenvalues are imaginary numbers, and that's strange, but we're going to see what that means. If we close our eyes and we plug in those eigenvalues, we find these eigenvectors, which also they have imaginary components, which is a bit strange, but we'll see why. Meanwhile, we're going to generalize it for any angle except 0 and pi. These are going to be the eigenvalues for any angle except 0 or pi. Well, now with those eigenvalues, I can find my eigenvectors, just as I did before, except I didn't find the null space. I just converted these to system linear equations. I factored out the sine of theta, and that's why it cannot be 0 or pi, because then sine of theta is going to be 0, and it's like you divide over 0, and you can't. I'm going to show why complex eigenvalues and eigenvectors kind of make sense. They kind of make sense because if this is the linear transformation, there does not exist any vector that stays in its own span. In fact, you can only think, I think, of a vector pointing in the axis of rotation as set vector. But of course, that's not a member of R2.